I'm Andrew, and I today am going to be talking about dynamic tracing. There's a question about what that is. First of all, there's a lot of content in the slides. If you want to follow along, feel free to scan the QR code. I'll leave it up for a second. And I will start the preface. So dynamic tracing, what do we mean by that? It's kind of two different terms here. Dynamic, I specifically will define to mean having the software tell you about things, data, its life cycle that it was not pre-programmed to tell you. Tracing, I'm not going to define so clearly. It's one of those, you know it when you see it. But I will say that it generally has themes of being very fine-grained and kind of full granularity information about some system. But it's an overloaded term. You know, OpenTelemetry says one thing, execution tracing, kernel scheduling tracing. All of these are tracing. And I can't bring up this topic without talking about dtrace and kind of the legacy of dynamic tracing for production use cases. This image on the right is Brian Cantrell in an iconic 2007 Google talk when he introduces dtrace. And in that, he has this kind of prefatory diatribe about what makes software so different from other engineering disciplines, in that software, unlike a building or a bridge, you can't see it. It doesn't attract mass. It doesn't give off heat. Those are kind of his words. You should watch that talk. It's a great talk. In this talk, I'm going to primarily focus on the dynamic aspect of dynamic tracing in terms of the techniques to dynamically change the behavior of code in order to get data and information from it. And I'm going to try to do that through the lens of tracing. So we'll see if I deliver on that. So specifically in the context of this talk, we're going to be looking at a Go program that is a total toy. It is a simple program that has an HTTP handler where it's going to record a time, it's going to call some simple function that's going to increment a counter, and then it's going to print how long that took. And we are going to then try to measure things about this program. So say we wanted to know what was going on with that counter. What would we reach for? One thing you might reach for, if I can find my controls, would be a debugger. And so here we'll see, okay, so first this is the program just running, and we can see kind of how long it takes to do this atomic increment. So we're in the order of 200 nanoseconds, and then later we do a bunch more, and you can see some caching effects that it gets down to like 50 nanoseconds. So that's kind of a baseline for us, and we'll look at that more deeply in a second. But then you might say, okay, what if I want to look at that counter with a debugger? So here again, we can now use delve, the Go debugger, and we can use its trace command. And every time it's called now, we get a little piece of output on the bottom. And it's not that useful because delve trace is sort of an afterthought. And so you get arguments, and you get the arguments that we passed in at the top. But then we disconnect and it crashes the program, and this is not something you're going to want to use in production. And I think I also want to bring up here that we went from 154 nanoseconds to 4 to 5 milliseconds. So that's quite a bit of overhead. Now we'll let this one restart. We can use a more fancy delve feature and give it an init script, and now we can actually print the expression for this counter, which is what we were after anyway. And here we do the same sort of thing, and the performance is the same, but at least now I'm getting the counter values. So great, I can see the state of the system as transactions are running. That's pretty cool, but it's very slow. Like we can't actually do this to our systems. Not to mention the crashing behavior if you're not extremely careful, though. I don't know how many of you have considered and then tried to connect a debugger to your running production system because you just can't figure out what's going wrong. So how can we understand kind of what's going on with this debugger? We're going to pull out a different tool called Magic Trace. I don't know, has anybody here ever used Magic Trace? Does anybody know what magic trace is? Cool, yeah. Well, I'm going to show you, or at least I'm going to attempt. So magic trace uses a Intel PT, which I think is the processor tracer, to give you like nanosecond instruction level granularity of the behavior of the computer, which is incredible. What a magic tracer. And so earlier we said we were going to record a time now, and then we're going to do an increment counter and then time since, and that was like 200 nanoseconds, and there you go. This is I didn't inject the debugger. And this is like a hint that maybe we could have nice things. I don't know. It's Chrome DevTools. Like, we could have nice things, but we don't. Do we? No. All right. Of course. Now, let's look at the same thing, but underneath Delve. So here, instead of that increment counter being 10 nanoseconds or whatever, it's huge. And just out of curiosity, you can start to build intuition about what else takes how long in your system. So here we see 2 milliseconds just for this first interrupt, which is not the whole thing even. And so what Delve is doing here is utilizing an int3 trap, which is a mechanism that the operating system offers to jump into the kernel and engage with external processes. And we'll look at the other side of this in a moment, but we can see that just a ton of time is spent unscheduled, and what is it doing? So now we can kind of take this same technology and look at a trace of the debugger. So here we can see these 4 milliseconds of the hitting of this trace point from Delve's perspective. And we can look very quickly. I mean, you might want to come back and look at these, and I'll post all the magic traces as well. But we can start to build intuition about this Delve debugger thing not being very efficient. This here, 1.3 milliseconds for find global internal as part of eval. Like, it's obvious that the debugger was not intended to be a high performance tracing tool. It's awesome that it works at all. We're very thankful for it, but it doesn't fit the bill of I want to understand the dynamics of my production system, both from a performance perspective and from a safety perspective. But magic trace, I mean, magic, right? Why don't we just all use magic trace for understanding our performance problems? It is actually very low overhead. Unfortunately, it requires bare metal access to a modern Intel machine on Linux, and it doesn't really work in cloud VMs. You can get a specific Amazon VM if you pay for bare metal where it can run, but for the most part, your production containerized environment, you're not going to get magic trace to work. Now, probably it's worth giving your engineers some desktop with nice tools like this. RR is another one, but it's not broadly available for your production issues. So, recapping on the debugger, it can give you access to the data. It is not performance optimized. It's missing workflows to utilize it in any kind of real or production setting, and it's scary. It's scary. You hold the thing wrong, your process is gone. So is there some other buzzy technology that can do better here? Well, there's this thing called eBPF. I'm not going to go too deep on what eBPF is, but it's a virtual machine embedded in the Linux kernel where the kernel says, I'll run this code in response to all kinds of different events. And one of those events, uprobes will explore a little bit further, where they run in response to arbitrary user instructions, effectively. And what's cool about eBPF is the kernel verifies and kind of proves that the program that you've injected is safe, for a definition of safe. And that's really excellent. So let's look at what we can do with a tool called bpftrace. I'm going to, no, I can't pause it. I should have, anyway. So here we have a little bpftrace script, and what it is going to do is record the counter when the request runs, but I just happen to know that it's sitting in arg2, which maps to a register. I could have named the register. I had to look at debug information for that. In different kind of programming environments, the ABI is clearer on where that argument's going to be, but it's a low-level tool here. It might feel higher level than a bytecode, but bpftrace is not a friendly debugger, let's say. You have to write these scripts, and you have to print to text and then parse what you've printed. But let's look at the overhead. It's really a very different level than what we saw with Delve. So we can see that it's single-digit-ish, approaching 10 microseconds. So we've gotten, what, 1,000 times faster? Now we're talking about maybe I can do this. Maybe I can just actually BPF trace my programs. And that's pretty cool. So we can also similarly magic trace our BPF, which is really sweet. And we can learn a lot about the underlying behavior of BPF probes and their performance profile. So we zoom in, and again we see this int3 handler. So the kernel is also injecting an int3 instruction and then running this BPF code instead of scheduling some other program to run. And we see those are 6 microseconds again. And we also will see that a lot of this time is in the trap handler and the deciding what probe I'm going to run. So there's 2 microseconds of setup, and then there's another almost 2 microseconds of teardown, and then the thing runs, and inside here actually most of the time is in this BPF ring buff output or commit, which is going to write that string to the output. The actual logic of this takes very little time, which maybe makes sense. So can we do more stuff? Can we get Delve-like, debugger-like functionality out of bpftrace? And here we have another version of this, but I'm going to print the stack, so it's going to walk the stack. That's a cool piece of functionality if we want to figure out who's calling some function, which, I don't know, that's a problem I've faced before. It's like, how do I get here? And now you could know. And you could amortize this. You could put the stack in a map and not output it every time, and that would be lower overhead. But we'll also see that there is more overhead. This is slower. And so here's a screenshot where I'm showing that grabbing that stack is like 3 mics. It's interesting that we fault here. You won't always fault walking a stack, but the kernel recovers because it's just going to follow the stack pointers. And then we can also say, I want to measure durations. So how would I do that? Maybe at the entry to the function, I'll record the time and put that in a map, a global variable effectively, that's keyed magically on some other key that I happen to know in Go in R14 on x86 is the Go routine pointer. So sweet, with some inside knowledge and this low-level tool, I can achieve a goal, seemingly. So this uret probe is a built-in feature where the kernel is supposed to call my function upon return of the outer function. This is pretty dope if I'm trying to understand the latency of some operation that is function scoped. And here we saw it attach 2 probes, but the timing was more or less twice the U probe. Unfortunately, this doesn't work in Go because the way this actually is implemented is it puts another call frame on the stack. And the Go runtime doesn't like that. So the function we were tracing before didn't allocate, and so it didn't interact with the garbage collector, and we were kind of felt safe, but in fact we're not. And so here I've changed the program to allocate underneath that function, and Go says no thanks. So bpftrace, as much as there's safety in BPF, there's not necessarily safety for your program in your runtime. Still very cool, very low overhead. Powerful and flexible programming environment. This is very much a derivative of dtrace for the Linux world, though Brian Cantrell will say that it's not as careful about dropping data. It's missing some niceties for user space. So one thing when you use bpftrace for kernel data structures is it has some awareness of what are the data structures in the kernel? Like, what is a task? What is a file? And so you can use like the names of fields for the most part if you've set things up correctly. For user space, that information is in the binary for the most part, but bpftrace support for using debug info to like access fields doesn't really, it's not there. There are cool tools to make it more of an applicable tool for like a cloud environment. So Inspector Gadget lets you use a variety of BPF-based and other instrumentation tools in Kubernetes clusters, and Pixie also. You should check those out if you haven't. They're very cool. And as we saw, it can have problems if you don't hold it correctly. You can also use eBPF without bpftrace, right? eBPF is just a low-level technology, and so I'll just briefly demonstrate a system a low-level component of a system we built that can extract the data for our request. So here we have just kind of some output of a probe that is not using bpftrace at all. It's using a completely separate system that is compiling eBPF externally and then distributing it and reading the value of our counter. All right, so eBPF considerations. You trap into the kernel, which has a performance floor for user space. You're going to pay the price for that trap no matter what. It requires effectively root in order to use it at all. There's an interesting project out of Red Hat to try to delegate that privilege to somebody else who you give root to, but that thing has been audited, perhaps by Trail of Bits, I don't know. Reading memory is another thing that can be rather slow. It, in general, doesn't want to fault, so it's going to check page tables for user reads. The verifier can be a painful thing, so the kernel doesn't want your program to run forever or do anything illegal, so it doesn't really want it looping in an unbounded way or accessing uninitialized memory, which sounds fine and good, but it means that writing those programs by hand can be quite painful. The uprobe API is rather surprising. It's oriented around object files and inodes rather than processes, so it doesn't really work for JITs very well, and I mean, it's really just like some kernel developer was like, well, don't you really want to just trace libc? And it's great for that, but for a lot of other use cases, it can be a little strange, and for Docker layers also strange. eBPF is evolving rapidly. There's a lot of new functionality coming down the pipe that makes it more powerful, that makes it more ergonomic, but you don't get to use them because nobody upgrades their kernels, right? Like, you follow the mailing list, and then you're like, cool, in 5 years, if I'm lucky. So in some ways, the innovation is left for people who manage their own kernels at hyperscalers like a Meta or a Google, who will backport patches, or you just live on the old one. So there are other techniques to achieve our goals. We can do some form of runtime binary patching. These are different projects of different kind of ages. BPF time is interesting in that it actually uses Frida under the hood, but tries to expose a BPF trace-like front end. I just thought it was relevant enough to talk about it. Valgrind is generally somewhat different, but all of them are trying to do some form of changing a binary from the inside in user space. Did I skip one? Okay, so we've also built a tool that allows you to do the same thing that we implemented in eBPF using Frida, which is a great toolkit. People should check it out. And the overheads on the kind of cold case end up looking very similar, interestingly. I want to say that I have not been scientific about latencies here at all, intentionally. This is really just to give you a feel for the sense and order of magnitude. But additionally, you'll see when we run it more parallel that the floor doesn't exist on how performant we can make this. I mean, we have full control. It's whatever the assembly needs to be. So here we can see two different magic traces of the slow path and the fast path, and it's a full order of magnitude different. People want to talk separately later about why and how to reason about this and cache efficiency of code. Love to chat about it. So binary patching techniques, they can be very fast. They also offer very flexible deployment possibilities because you don't necessarily need root. You can have different kind of privilege models to utilize ptrace, and there are lots of ways to achieve that. You can statically relink something, you can add a library, you can have an exec wrapper, you could have some privileged agent, you could do the BPF man thing, ptrace me, I don't know. And safety is possible. The difference here with the eBPF is the kernel developers are trying to make it safe for you, and here you're kind of off the rails. So it's all a question of how well you've done the engineering. Parting thoughts on the talk. The building blocks exist to build efficient, safe, low overhead dynamic tracing. It's a complex landscape of trade-offs around privileges, efficiency, expressivity, safety, performance. There's still a lot of engineering required to realize a vision that you can fearlessly ask anything of your running programs. And there's just a lot of problems to solve in order to do that. Loose coupling between these programs as the code changes. Can I reuse my probes from last week, last month, last year? What do I do with the data that I've gotten out of that program? Is it sensitive? Where should it live? How do I make expressive probes? How do I ask the question I want to ask? How do I ask it quickly, effectively? How do I collaborate with my teammates about what questions we want to ask and problems we want to solve? How do I analyze the data that comes back out? What should the data model be? How do I make it ergonomic for different languages and language runtimes? And what are other signals that correlate with dynamic instrumentation data like runtime tracing, kernel tracing, syscall tracing, CPU profiling, snapshots, HTTP endpoints of some debug page? You know, how does it all fit together harmoniously to tell us what the software is doing? So that's what I've got. Thank you all very much. We are trying to realize this vision with our project called Side-Eye. And I'd love to answer any questions.
When you get the question, can you repeat it into the mic?
Sure. Yeah, go for it, and I'll try to repeat it. I don't know. Should I come?
Yeah. So what are the prospects for improving performance on sort of both the sort of attaching eBPF probes to processes on the system, and also, I mean, like, so I've used the sort of perfect eBPF infrastructure on a sort of critical sections that are like not 50 nanoseconds, like 100, and it blows things up. It's really not, it can't be used for production. Maybe it's the part you can use on a performance environment. So is the only alternative you see in the future binary patching, or are there initiatives in the kernel development space to reduce the overhead of both setting up eBPF probe and doing the work inside the eBPF version?
Okay, so the question, as I understand it, is whether there are projects underway within the Linux developer community to make uprobes more efficient for performance sensitive and low latency critical sections, or whether any alternatives will emerge to achieve dynamic tracing other than using uprobes. There's some talk on the mailing list of different types of approaches. One thing that's really not been clear is how to separate things like accessing BPF maps and k-funcs and general helper functions that assume they are operating in the context of kernel space. I think that if you're going to trap into the kernel, you're in trouble, or at least you're just not going to get the performance that you want, just because of the cost of that trap and spilling the context, I think. So it's not totally clear to me. There's been some discussion of can we have user space only maps that are mem-mapped back into the process, but I don't know of any immediate progress on that. And the separate point would be, even if it does happen, when do people upgrade their kernels? Yeah.
What's Frida?
Frida is a dynamic instrumentation toolkit, often used for security use cases. So for Frida has an interceptor framework, and it also has this like call tracing framework where it'll try to get complete function call tracing. It is not particularly performance concerned, so there's some space there. The Frida project is relatively large in that there's pieces about injecting Frida into a program from the outside, and then there's stuff to run on the outside. Frida as a whole is actually generally interacted with through a JavaScript API because they inject like V8 or QuickJS into the target program. So you write your probes in JavaScript, which is very cool, but is often used as a research tool more than as a dynamic instrumentation tool. It's a great project. It's a passion project by really one guy for now some 12, 13 years. Yeah. Any other questions?
With binary patching, if that's the project you are going with, is this not a problem for like compliance? Like, are there not security things that want to say we signed this binary and it didn't change, and if it did change, that's a really bad thing?
There certainly are some like code signing security boundaries and like control flow integrity systems in place. They may need to be disabled or coordinated with. The hope of our tool is to offer both BPF and a binary patching-based approach. One really key thing with BPF is that it only runs in Linux. And so if you want to make a tool that developers can play with on a Mac laptop, you need a different approach. And so at SideEye, our goal is to offer different options for different people who have different security considerations and different kind of runtime needs. And we strive to have a uniform experience, whether you want it to be driven on a Frida backend or a BPF backend. All right. Thanks, everybody.
Thank you, Andrew. We're going to take a 5-minute break before we get going with the next speakers.